Hi, I'm Hans-Jörg Heisch. I'm a project manager for coherent test solutions in Keysight. The application that I'm going to present today is a new arbitrary waveform generator which is capable for testing coherent digital signal processors. The challenge for developing digital signal processors for coherent test is that those digital signal processors can compensate impairments that occur on a fiber transmission. The challenge for those developers is that those DSPs have to react to time-varying impairments on a fiber transmission. The beauty of this new instrument, the M8195, together with the optical modulation generation software, is that we can generate waveforms in real time and change the properties of the signals that we generated at runtime. And I will show you the setup as follows. Here we have the arbitrary waveform generator, and the signals that are generated, the electrical signals, they are then sent to an optical multi-format transmitter which converts the electrical signals to optics. Then the generated signal then goes to an optical modulation analyzer, which then analyzes the signal, the properties of signal, and the quality of the signal. Okay, the first experiment that I'm going to show is that we can generate a QPSK signal in real time and then change the signal from a QPSK to a QAM16 signal. On the M8195, we do not store waveform samples, but we just store the information in terms of symbols on the memory. And then from the memory, you play the symbols, and in a real-time encoder, you generate the QPSK or the 16 QAM signal. And what I'm showing you now, I have a QPSK signal set up, and now I will just change the signal to a QAM16 signal. Okay, the first application of impairment generation will be generation of phase noise. That means synthesizing phase noise electronically. You know, in DSP, in the coherent receiver DSP, there's always a phase tracking algorithm which tries to catch the changing optical phase either of a local oscillator in the coherent receiver or of the signal laser that sits at the other end. What I'm now showing you is that you can change, switch on and switch off the properties of phase noise in this application. So what we have here on this screen is the display for the phase noise application. What we have up here is the phase noise property, the phase noise power spectral density for a 1 megahertz line width laser. And below here you see the phase trajectory that we synthesize in this application. Now the phase noise generation is switched off, and you see this on a clear constellation. And now I will switch on the phase noise generation. And you immediately see that the constellation changes and it's no longer clear as it was before. So, and now I switch it off again, and you really see that it's all done at runtime. The second application I will show you is the generation of polarization mode dispersion electronically. We have implemented a standard literature model of concatenated elements of birefringent crystals, and we have actually the algorithmic representation of those, and we have implemented those representation in a DSP in the M8195. And now by just setting the combination of the birefringent elements, you can now generate any polarization mode dispersion of first and second order. The maximum first order polarization mode dispersion is up to more than 200 picoseconds, and the second order polarization mode dispersion goes up to more than 12,000 picoseconds squared. Now I'm going to show you the impact of polarization mode dispersion on the constellation. I'm just switching on the PMD and you clearly see that the constellation changes, and we now, when changing and switching on, it really represents a time varying behavior on the network. So the compensation algorithms in the DSP has to cope with the changing polarization mode dispersion and tries to compensate it. Third application I'm going to show is that we synthesize polarization rotation electronically. This is really a challenge in DSP algorithms, how to cope with the fast changing polarization changes on the network. Usually optical polarization controllers, they are limited in speed. However, in a real network, there's very, very fast changing polarizations, like changing polarizations in the kilohertz or kilowatt range. Now, by electronically changing and electronically synthesizing polarization, you can repeatedly change the polarization and repeat patterns and lock the patterns to a bit error ratio measurement on your receiver. So whenever a bit error occurs or bit error bursts, that means that your compensation algorithm cannot cope with the polarization rotation that occurs on the network. Now, when you optimize your algorithms, you can repeatedly start the polarization rotation patterns and repeatedly always synthesize the conditions under which your algorithms might fail, or after you have improved them, you can really check how robust they are against these fast changing polarizations. Now on this arbitrary waveform generator where we synthesize these changes in polarization, for instance, in this application, we show a great circle on the Poincare sphere, and on the optical modulation analyzer, we have the corresponding analysis tools where we can now change and analyze the polarization, how it comes into the analyzer. Okay, I have shown you a few application examples of the arbitrary waveform generator M8195 in conjunction with the optical modulation generation software under the product name 81195A. If you'd like to have more information about these products, please visit our Keysight website. Thank you for listening.